This is our team's final presentation for our project. We took track 2, face swapping. My name is Matt. Also on the team are Nikhil and Shiv. I'm going to take this opportunity to support what we had in our final report with visual representations of our methods and algorithms. So let's get into it. First, starting with our basic outline, we first interpolate to match the length of the source to the target if necessary. And then if there are multiple faces in the video that will be detected, we want to choose one to track specifically. We then move into the main loop. So the frame resolutions are matched. The features are extracted. This is probably the most involved step that I'll get into later. We then warp the source to the target. The source, to clarify, being the frame that has the face that we're going to warp onto the target frame. So the source has the replacement face on it. And then finally, the face from the source will be blended onto the frame from the target, and that frame will be written to the output video. And then we start back up at the beginning of the loop with the scaling of the frames. So let's go through each one of these steps in more detail, starting with interpolation. Interpolation is a step that's not always necessary. The target video is assumed to be of desired length. So if necessary, we extend the length of the source to match the target. So to do that, here the source is Frank Underwood, the target is Mr. Robot, and at the beginning, the source is shorter than the target by a few frames. So all we do is use a weighted average to lengthen the source to be the same length as the target. The next step in the process is face detection. So for example, in the video with Leonardo DiCaprio, there are multiple faces. Not all of them will be detected, but a few of them will over the course of the video. So we need to pick one that we want to track. So for that, we use something from OpenCV called Cascade Classifier at the very beginning of the video. And that pulls out Leonardo DiCaprio's face specifically. So that's the bounding box that we want to accept features for, and any other features that are found during the actual loop that are outside of that bounding box are discarded. And that bounding box is updated from frame to frame as we go along to make sure that we're tracking, we're keeping the features that we want. The next step brings us into the actual loop, first step being frame scaling. So this is a simple step that uses a method from scikit-image to scale down the images to be the same size using Laplacian pyramids. For runtime, whether the source of the target is smaller, we're going to go with the size of the image that is smaller. The next step is the most involved process throughout this project. So I'll first go through an overview of this process flow and then have a visual representation of some of the things that are happening. So we use dlib on features that are gotten from images that have been contrast limited adaptive histogram equalized. That improves feature recognition rate. So there are a few conditions before we pass the image to be low pass filtered, pass the features in the image to be low pass filtered. First, if no features are found, we care about whether we have features in the previous frame or not. If we do, then we can use optical flow to flow those features forward in time to the current frame. However, if we don't have features in the previous frame, then we're going to save this frame and whatever features we have, either for the source of the target, and we're going to save that because the next time around the loop, once we find features, we can use backwards optical flow. So you can pass those frames that we saved and those features that we saved into a function that's going to try to get some of those frames back. So specifically for the dlib features that are found, these are features that are numbered so that correspondence can be ensured. We used the outline of the face for warping, which you'll see later, and then the green features you see in the image are ones we did not use for optical flow because they proved to be too unreliable. Okay, so now let's get to the complicated part. When we don't recognize features. So say we're going along and we're recognizing features just fine. Then a frame happens where we don't have features. Okay, so then we look at the previous frame, and if we can, we flow those features forward in time. Now, as you can see, this doesn't always work out so well. We throw out features that exceed a certain distance from their corresponding feature in the previous frame, and so usually at a certain point we can't flow forward anymore. We've lost too many features. So that frame gets set aside, right? And then say there are a few more frames that we miss. So now we have this list of frames with no features. So we're going to wait until we find a frame that we do have features for. And then we're going to pass that frame into the optical flow backward function and try to take those features and flow them back. And it'll work for a couple or a few, but if there are too many frames, we'll just end up writing those frames to the output video without the faces swapped. At that point, once we've written all the frames that we missed to the output video, we can proceed to the face warping step. Okay, so this, we use the outline of the face, the features on the outline, not the features on the inside, to create an affine warp between the source and the target. That affine warp is applied, and then we use the features, some of the features from the outline, as well as the features from the inside to actually do the warping step. So for this, we adapted what we'd written for Project 2A to actually perform the warping. So this is done on just the window around the faces that contains both faces. This way we reduce runtime. So we take a look at both the source, the target window. We create a Delaunay triangulation from the features from the source frame, and then we morph to the features from the target window. And but the cross dissolve fraction is 0 because we're going to keep the face from the source window. The final step in this process is blending those two images together. So starting with the original source window, it's matched color-wise using a histogram matching algorithm. Now this is done kind of during the morphing step, so there's a little bit of overlap here. Then a mask is created based on the features after the morphing is completed. The two faces are swapped and cloned using OpenCV's seamless cloning function that uses Poisson blending. And because we wanted to make that transition a little more seamless, we did a little bit of alpha blending. So we created a mask with a smooth lead-in that, once applied, it kind of smooths those edges out a bit along the face, especially when the faces don't quite line up. This really helps with the final appearance. So let me explain a little bit further how we generated that alpha mask. So we start with the original mask, and then we basically want to use a distance transform like algorithm to generate 4 images. So this is done in 2 loops, moving from left and to right, and then from top and bottom. And instead of doing the simple distance transform, you're trying to generate a dissolve fraction as you go along. So you're taking a fraction of the mask image, and then it's a dynamic programming algorithm, so you're also adding the fraction from the row or column previous. And so the result of this is that you put all these 4 frames together, you take the minimum at each step, and then you clip between 0 and 1, and then you have this alpha mask that you can use to cross-dissolve the 2 images. That is the final step. So at this point, we've gone through the whole process flow. That frame would be saved to the output video, and we'd start back up at the frame scaling step. In summary, we used several open source libraries to execute these algorithms and methods that we've described, such as OpenCV, scikit-image, dlib, as well as scipy. The algorithms and methods that we used include several that we studied over the course of the semester, like weighted averaging for interpolation, as well as filtering, nearest neighbors, Laplace pyramids, the optical flow algorithm, as well as least squares, Delaunay, triangulation, as well as gradient blending and the distance transform. We also use some new ones, specifically the histogram matching algorithms that we use to adjust for lighting. Overall, this was a really fun project. We got to use most of the things that we learned over the course of the semester, as well as learn some new things. So thank you very much for listening to this presentation. And up next are the video results that we achieved. Thanks.